All right, everything's graded. It's all there on the table, so grab it if you want it. The final is open notes and open books, so you might want some of that stuff. Up to you.
When is it?
So I have it on Tuesday, and that's actually not where the schedule has it. The schedule has it on Thursday, so I need to know if there's conflict. Like, look at your finals, because if Tuesday doesn't work, then we'll have it on Thursday, the 13th. So that'll be on you to look at your finals and then communicate with me if Tuesday does not work, but it's 1 to 3 on Tuesday.
1 to 3.
Yeah, it's 2-hour final. Of course, you want to have the full amount of time, the full experience, right? We will review for it here on Thursday, which will be a lot like today, which is pretty much review. New topic of deflection, but other than that, you know, bending stress, shear stress.
If I'm working with SolidWorks, it's okay. Can I also, can I work on the classroom that day?
Like before one,
Yeah,
if you like,
if I finish the song.
if you communicate with me, yeah. If you want to take it earlier on Tuesday, that's fine. Just communicate with me so I'm here. I mean, I'm gonna be here at 9, I think, on Tuesday, so. Yeah. In-person final for those of you in like online land out there. I want to have it in person. If you can't be here, let me know. Good. Homework is 15, 7, and 9. We're gonna do deflection. I'm just gonna work a problem kind of start to finish where we do the statics, and then we do the bending stress, and then we do the shear stress, and then we do deflection. So we are gonna do deflection by formula method. So I'll talk about that. All right, you good? Oh, I sent out an email. You probably saw it or you didn't see it. You will see it. Any late work that you want to submit's got to be in by Friday of this week. So if I don't set that deadline, then people start throwing me stuff during finals week. That's not cool. So anything that you want to submit that's late, do it by Friday, por favor. All right, good? Questions? No. Perfect. All right, here's the problem. It's number 36, but it's a little bit adjusted from what 36 says. So I think that's out of chapter 15. We're moving into 15. So let me check and see that it's out of that chapter. 6, yeah, it is. So it is an aluminum beam. It has an inertia of 200 inches to the 4th. So we don't know the shape. We just know that it's got an inertia of this and it's got a Q of this. Q is area moment of inertia, and we use that in shear stress. So that's why I'm giving you Q. The problem doesn't give you Q, but it does say calculate the maximum deflection. Before you calculate a deflection, you always calculate your stresses first, because if it's overstressed, then you can't do a deflection. It's not valid. So typical finals type of problem where you have to do a few things. We have to do bending stress. We want to calculate the maximum deflection. They do give us a limit of 1 to 300 of the span. That's a pretty common deflection limit. 1/300th of the span. So in this case, the span is 6 feet. So if you take 6 feet and do 1/300th or divide by 72 inches divided by 300 is, well, that's 72 divide, it's 0.24, about a 1/4 inch. So in a lot of industries, that is a acceptable deflection. So we're gonna work through the statics. We're gonna work through the shear moment diagram. We're gonna work through bending stress and shear stress first. 2,000 pounds at the very end. 1,000 pounds per foot for 3 feet. And this is fixed. So it gets a Y, X, and a moment. So I'll call it moment A. We'll call this AX, and we'll call this AY. So we need a Y. We can sum forces at Y. AY is 5,000. We have no X forces, so AX is equal to 0. And then what's MA equal to? Some moments about A. Oops, 2,000 times 6 feet. And that is positive. 1,000 times 3 times 1.5. Right, the 1,000 times 3 concentrates it halfway, 1.5. That's also plus. And then this is going the other way, right? It's negative moment at A, and that's equal to 0. So that's how you write it with a fixed support. You label your moment, whatever you label it, and you assume the direction, and if everything comes out positive, then you're good. The direction's good, and you can calculate MA. $16,500. Foot-pounds. So like on the final, the problem would probably say, you know, calculate all these things and also draw the shear and moment diagram. So we will do that.
Then we're doing this one's like.
I know, that's why you got 2 hours. You know, 8 problems, 15 minutes a problem.
No, what?
Yeah, you gotta grind it out.
That's crazy.
No, it's not. Good.
Next Tuesday?
Tuesday at 1 o'clock. If it doesn't, if that doesn't work, let me know. Because I am not following the final schedule. Don't turn me in, but final schedule has us doing it on Thursday at 1.
Would it be possible for me to take it online? Because
In class. You can take it at a different time if that doesn't work. So I think one might go early. I'm here at 9 on Tuesday, so you could do it at 9. Or a different day. You just gotta let me know.
I'll send you a message.
All right. Yep. Yeah, no problem. Shear diagram. You do it. You probably have it done. Rock stars. Comes down. Nothing happens, so it goes straight across. And then it comes down. Then it goes up. This should be 2,000. And then it drops a total of 3,000 to 5,000. And then it returns Vmax is 5,000 tons. Then I'm going to superimpose the moment diagram on top of the shear diagram. So it's just so fun to do that. So then the green equals M equals 0. And it is 0 out here, right? The shear diagram is negative, 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 and then it gets more negative. So it's going to start at a slope. I'm going to keep it pretty flat. To here. And what's the moment? What's the moment at this location? Equal to? Careful. Yeah, it's just this rectangle right here, 2,000 times 3. So that is 6,000 foot-pounds. So I'm just superimposing the moment diagram on top of the shear diagram. Then it goes more negative slope, and then it's continuously getting bigger and bigger negative. So it's coming out of here like that, and then it's getting steeper and steeper and steeper. So, and it is parabolic down to there. And we know if we're confident in our moment calculation up here, that it should be 16.5, because that's the moment at this location. We're at the same location.
Sorry to interrupt. The question again. Exams open up, right?
Open note, open book.
Thank
you. Yep.
I think put an extra 0.
You think what?
They put an extra 0,
Oh,
I think. And then
yeah.
it's 2
I have a whole bunch of zeros there. Here, I'll put a decimal point in there. It's like money. 16,500 foot-pounds. Good? Clearly the maximum moment. All cantilevers have, this is a cantilever, no support out here. All cantilevers have maximum moment right here. So all cantilevers, unless you have some kind of up force, they're all going to deflect like this. And that is a frowny face. So that is a negative moment. It's all down here negative, right? So there's a bunch of things that help you out with cantilevers. I guess you could have an upload and it could deflect up, but that's pretty weird. Pretty rare. All right, so now we can go for shear stress max, which is VQ over IB. And we don't know B because we don't know the shape. So I actually just kind of threw this whole shear stress thing in. So we'll say that this thing is like some kind of a W shape, right? And here's the neutral axis, and B is the width at the neutral axis, and we'll say that that is 0.6 inches. So that's what B is. It's the width at the neutral axis, because shear stress is maximized at the neutral axis. Bending stress is maximized at the outermost fiber. Okay, and we'll say our C value is 7 inches. We'll need that too. So I just kind of made this up. We have Q, we have I. Yeah,
I had some difficulties doing the homework from last week. Trying to find the Y bar of a W. So we were supposed to add the area 1, area 2, right?
mhm,
The area 1 on top is the same as the box, so you just add them up.
yep, yep.
Is there?
When you do the area moment, the Q, you can split the areas up. So you can do that area times its distance, and you can do this area times this distance. That's a little easier than trying to combine.
I see.
Yep, just break them up.
So you just, wait, did you find the Q,
The Q is given.
like in the book, or you just get?
I just made this up, yeah.
Okay.
And that'll happen on the final too,
You're
like
just gonna make it up.
to save time, I will give you Q.
Oh.
So you don't have to calculate, right? So, and to save time, they've given us I. So that's how I can shorten problems, is by giving you all the properties, not making you look them up or calculate them. So look for that, like, hey, if they're gonna give it to you, then just use it, don't recalculate it, right? If they're gonna give you I, don't go looking it up, or don't calculate it. If they're gonna give you Q for the shape, then they're just helping you. Alright. Maximum shear is 5,000 pounds. Q is given at 4 inches cubed. I is given at 200 inches to the 4th. And the base dimension at their neutral axis was given as 0.6. Like, the problem can give you a lot of stuff, especially on the final. You could have the thermal coefficient of expansion for the material. You could have Poisson's ratio for the material. All these things that we've like dealt with in the past could show up on that problem. That doesn't mean you have to use it. Don't use it if you don't need it. Just use what you need. All right. How's our units here? Inches to the 5th, inches to the 3rd, so we're at PSI. So that's good. Keep track of your units. Okay. You get 166.67 PSI. And what does aluminum think of that? So you'll probably also be given the limits if there's not any in the back of the book. And I don't think aluminum has any shear stress limits in the back. It doesn't. So it just has ultimate. Does it have it for aluminum? Yeah, 27 for 6061. 27,000. Yeah, 27 KSI or 27,000 PSI. That's pretty big. How much do we have? 166. So do we have a shear problem? No. We are factors of safety to the good.
Did you say do bending first on the video?
Yep, bending typically you do first. Check it in shear, but you're gonna do both, so I just did this one first. Yeah. If you gotta do them both, doesn't matter what order.
Okay.
Yeah. All right, so bending is what?
Let me see.
MC over I. Or M over SX if we had SX. Some of you used that. That was good. But we don't have SX. We have I. So we'll use MC over I. What's our moment? $16,500. And that is what? Foot pounds. So again, keep track of your units. This is where the opportunity is to mess up. What's our C value? I gave it to you as 7 inches. You get that from the shape, the C value. And then we're given I at 200 inches to the 4th. Bending stress needs to be in PSI, pounds per square inch, or KSI, kips per square inch, either one. We have pounds, but we have a foot mixed in, so that's got to go away. 12 inches per foot. Almost always the case that we have to add this to get our units to work. Six nine three oh. What's the aluminum's yield stress? $35 or 35,000 PSI. So how is our stress? It's good. What's the factor of safety?
35,000, but 60.
Yep.
6.
Yep. .05, or basically 5. All right. So everything's good. We're within stress limits. Everything checks out. Now we can do deflection. So we are doing deflection by the formula method, not the area moment method. Area moment method is pretty complicated. It's really like not necessary for us to grind through. The more common method is the formula method. And there are a few in the back of the book, not all of them. So you can get more of these beam diagrams online. Just be careful of your source. But these are called beam diagrams and formulas. So in the back of the book, there are beams that are given that are super common. Like we do them over and over and over. So they generate formulas for you. They're super handy. And you get a bunch of information from this. So you can get shear and moment diagrams. That's cool. You can get maximum moment by formula. You can get moment at any X location on the beam by formula. You can get deflection. You can get deflection max. That's what that triangle is, deflection. And this is saying that it happens to be at the center for this very simple beam. Simple beam is reaction at both ends and then a distribution, a uniform distribution. So the key is your beam has to perfectly match these beams. It cannot be any different. So if you have a uniform load on a simple span where the supports are at the end, that's a match right there, right? If you have a non-uniform load, simple span where the supports are at the end, that's a match. Boom. Okay. You can also get deflection at any location X. Any location X. These get pretty gnarly, these equations, right? So W is the distribution. L is the span, so you can see L is there. So you gotta look at the diagram to see what they're calling L, what they're calling X, what they're calling W. And then also you're gonna need the inertia of the shape. So if it's a rectangle, you gotta know the inertia, calculate it, and you gotta know what the material is. E, modulus elasticity. So all those things typically are given in an analysis problem where you're given everything. You're given the beam, you're given the load, you're given the conditions, and you're asked, is it good? Is it safe? So our job is to match up what we have to a beam in the back of the book if we want to use the formula method. If you can't match it up, then you can't use the formula method. Now, there is a concept called superposition. That means if you can match up the beam to the back of the book with one of the loads, and you can match up the beam with the back of the book with a different load, and their deflection is maximized at the same location, you can use both of them and add them together. I don't know if that made sense, but so there is a cantilever with a single load at the end. Which one is it? Huh? 14. I agree. Cantilever. So we can match the beam. Come on, focus. There we go. We can match the beam and the load. So the beam is the same and the load. So we have a formula for this condition. Now, is there one with a partial distribution on a cantilever? 12 is a full distribution. So 12 doesn't work. There is none. There is no cantilever with a partial distribution, but there is a cantilever with a concentration. Yeah, that we can concentrate the distribution. Yep. Exactly. So cantilever beam concentrated load at any point. We're going to have a concentrated load at 3 feet, right? Because we can take this distribution and concentrate it. Both of those deflections, so this deflection is max at the fixed end. Oh, that's the moment. At the free end. Deflection maxed at the free end. Deflection maxed at the free end. That's also got to be true to use superposition. Like the deflection has to be maximized at the same location. All right, so we can do it. We can do this one. What's the equation? Oh, this one. Where's the single one? 14? Oh, there it is. We'll do this one first. PL cubed 3EI for maximum deflection. PL cubed 3EI. So this is going to be deflection for the 2,000 pounds. It's PL cubed 3EI. What's P? If you look at the diagram, that's the load, right? 2,000 pounds. Huh? I think so. PL to the third power of 3, 3EI. Yep. What's my L? Yeah, 6 feet, but E is going to be in inches squared. I is going to be inches to the 4th. So I would put L in inches. Yeah, 72 inches. That just solves that foot problem right away. Don't forget to cube it. 3 is a constant. What's E for what? How do we get E? For what material? Aluminum, yeah, whatever material you got. So what do we got for E? How much?
10,000 KSL.
10,000 KSI. We have pounds above, so we want it in PSI. So it's 10 million. 10 million pounds per inch squared. Good. And then what's our I? Yeah, 200 inches to the fourth. All right, good luck running that. That's what I get. Did anyone else get that?
I did.
Oh, good. It's brackets.
Yeah,
It's always brackets and a TI.
I just put them in.
I think that's wise. I think that's a good way to do it. I would do this first. Yeah. Yep. All right, so the other one is this gnarly one. Concentration at any X location. It's that equation, max at the free end. PB squared, and it gives you B here. 6EI, 3L minus B. So we need this B dimension. Delta max at the free end, PB squared, 6EI.
Would the B be at like 1.5?
Yeah, so the B is gonna be, because here's our concentration, right? And yeah, 1.5 feet. Or what? 18 inches? Oops, sorry, 1.5 feet, 18 inches. 12 plus 6. All right, so now we're gonna go for, our concentration is 3,000. So I'll call the deflection 3,000. So the load is 3,000 pounds. So the B dimension is 18 inches. PB, and that is squared. Don't forget to square it. Over 6EI, 6. We know E is 10 e to the 6th, and that's in PSI. And we know I is 200 inches to the 4th. Now we're going to multiply it times 3L. And look at the diagram and make sure what L is. L is the full distance. Full distance. So that's 72. So 3 times 72 inches minus 18 inches. PB squared, 6EI down below, 3L minus E. Some super smart folks created these formulas for us, so we just use them. You gotta just use them. You gotta watch our units though. So we have pounds, and then down below we have pounds per inch squared. That's good. The pounds go away. We got inches to the 6 down here, inches squared up here. So we're gonna put inches to the 4th, and then that goes away. Should be good. Should be back to inches. All right, let's grind this one. Absolute deflection for sure.
These are mainly overstatics, these are, well, kind of overlaps, but.
Sex is fine.
What do you get? What do you get for a deflection?
0.016.
Yep,
0.008.
Well,
I got 0.16. You got 0.16? Oh, we're getting a quorum of 0.16s. So they're both at the end, so we can add them up. .14 inches, right? And if the limit given was 1/300th, 1/300th of the span, that's a pretty common limit. 72, 300 divide, that was a 1/4 inch, 0.24. We're at 0.14. So we would meet that
wait, what did you say?
limit. Huh?
What did you say?
I said that if our limit was this 1/300th of the span, that's kind of how they give a limit of deflection. Like it can't deflect more than 1/300th of the span. The span's 72 inches. So you take 72 divided by 300 and you get 0.24.
Oh, and it can't be.
That would be the limit. Any more than that and it's a failure. So it can fail in bending stress. It did not, like not even close. It can fail in shear stress. It did not even close. Or it can fail in deflection. It didn't. This thing is good. Huh? Yeah, super strong. I mean, inertia of 200 is pretty big. So that's an indicator right there that you have a lot of resistance to bending. If you have a inertia of 6, then it's like, oh, I'm not going to carry much load. All right, you have a couple homework problems in deflection to do for Thursday. Nice job. We'll do more.